So thanks everyone for following our paper later, multi-objective backdoor attack via evolutionary algorithm. This is joint work with Yan Qiqiao, Wang Kaitai Liang, and Yoko Smardex from Delft University of Technology. So first, let's start with some background knowledge. So this paper focuses on the backdoor attack in computer vision task. We have two stages. In the first stage, the train stage, we use the clean images and poison images to train the module, so that in the inference stage, our goal is that the trained poison module behave normally with the clean data, but shows the backdoor behavior with the attacker desired label on the poison data. And meanwhile, we use the discrete cosine transform to manipulate the trigger. So the process is we use DCT to convert the image into the spectrum, and we insert our frequency trigger, and we use the inverse discrete cosine transform to get the original image. Just to add some details here, in the DCT decomposition, for each row or for each column of the image in the spatial domain, we decompose it into multiple cosine functions, and we record the coefficients into the spectrum. And we sum up the coefficients of all the rows and columns to get the spectrum. So some background information. Well, this paper considers multiple backdoor attack objectives, include the robustness, the stealthiness, attack effectiveness, and benign accuracy. The first objective is the robustness. So in DCT spectrum, most of the low frequency information are concentrated in the top left corner. And we observe that these low-frequency information are very resilient against the image preprocessings. Here I show an example, the well-known BATnet trigger spread across the entire spectrum, and when we apply the Gaussian filter, you can see the medium and the high-frequency information are destroyed in the center and the bottom right side, but the low-frequency signal are still here. So based on this observation, we design our robustness to be the distance of trigger perturbations to the top left corner, which means we minimize the Euclidean distance of all the perturbations to the lowest frequency band. And the second objective is stealthiness. We consider stealthiness in dual domains, the spatial domain and the spectral domain. In particular, we use LP norm to restrict the trigger perturbations, and in particular, we use P equals 2 because we observe that the L2 norm of trigger perturbation in dual domains are consistent, which is our optimization process. And meanwhile, we guarantee the attack effectiveness and the functionality. In detail, we shuffle the train data set, and we divide into the clean and poison images. For the poison images, we insert our frequency trigger and manipulate the label to be the attacker desired one, and we minimize the loss function regarding the mixed data set as the normal backdoor attack. However, optimizing the above objectives is difficult. Taking two objectives balanced with the parameter alpha, for example, as people commonly use the Lagrange multiplier and gradient descent here, we show the objective quality of the trigger stealthiness and the attack success rate here in blue and red respectively. Note that the bar here indicates the standard deviation of 10 repetitions, and the objective value here, the smaller the better here. And in the left side of the figure, we see that the objective of trigger stealthiness and attack success rate shows monotonic trend, but in the totally opposite trend. So this result tells us the objective of trigger stealthiness and attack success rate are conflict with each other. And we sample the parameter alpha between 0.4 and 0.5 in a fine scale, and we see the bar here, I mean the standard deviation here, is remarkably enlarged. And these results show that the Lagrange multiplier and the SGD, which we commonly use for optimization, cannot stably produce stealthy and effective triggers. Different from that, in this paper, we consider multiple backdoor attack objectives. We optimize it simultaneously without aggregation. In specific, we use evolutionary algorithm for optimization rather than gradient descent. So evolutionary algorithm, abbreviated EA, is a gradient-free optimization method which maintains a population of triggers and drives the triggers toward the promising area and eventually leads to the practical triggers. First, the evolutionary algorithm randomly initialized a population of triggers, and it evaluates the trigger quality. It calculates the objective values, which I mentioned previously, the robustness, the stealthiness, the attack effectiveness, something. And these values will represent the trigger quality. Then the evolutionary algorithm will repeatedly apply the variation on triggers from the current population to produce the offspring triggers and hopefully to get triggers in better quality. Just to add some more details here, for each trigger, we encode it into the magnitude of perturbations in the spectrum, as well as the frequency band, I mean the location where you insert the trigger perturbations on. And we apply a crossover operation between two triggers, which exchange the magnitude and the location, and we apply the mutation operator to each trigger which randomly perturb the perturbation or the location. And finally, to get the offspring triggers, to evolve these triggers. Directly applying evolutionary algorithm for the trigger optimization is not enough. We observe that in evolutionary, there are some triggers that have the equal quality from the evolutionary algorithm perspective, but are impractical in backdoor attack. As I show here with the right arrow, there are some red dots which represent the objective values of the impractical triggers. They are either not stealthy or not effective. To address this problem, we integrate the preference-based selection mechanism, which calculates the distance of triggers towards the promising area. And we prioritize those triggers that are close to the ideal region and penalize those triggers that are far from this region. And finally, after multiple iterations, we obtain the final trigger population. And we choose the best trigger from the population based on whose objective values are closest to the best value for each objective. And we release the poison dataset injected by the trigger. So a poor person who downloads this poison dataset from the website to train their private model, unfortunately will get a poisoned model. And finally, we evaluate our backdoor attack with several metrics for the attack effectiveness and for the functionality. We use the ACC and ASR, which reflects the proportion of data that are correctly being classified. And for the stealthiness, we use the PSNR, SSIM, LPIPS, and L2 norm to comprehensively evaluate the stealthiness in either the spatial domain or spectral domain. For the robustness, we use the attack success rate after image preprocessing to reflect the ability that triggers resist the image preprocessing operations. So first, we show the stealthiness achieved by our ladder method and the other comparison methods against 5 data sets. we can see that in most results, our method achieved the best stealthiness regarding the full matrix. We also visualize the poison image in both domains. We can see the poison image and the disparity of the frequency spectrum obtained by our method is you cannot almost detect any anomaly. We also evaluate the robustness of our method against multiple image preprocessings like Gaussian filter, linear filter, and the results suggest that our trigger design maintains a high attack success rate after the image preprocessing operations. We also evaluate the attack effectiveness and accuracy. The results show that our method achieves satisfied attack success rate above 99% without sacrificing the benign accuracy significantly. And finally, we did the application study. We test if our method can still achieve all the objective performance without any one or multiple objectives. The result confirmed that all our objectives in our trigger design are necessary to get the final, the superior performance. So the takeaway is we consider multiple attack objectives and we observe the conflict among objectives. And we find that optimizing conflicting objectives with the commonly used Lagrange multiplier and the stochastic gradient descent is difficult. So we formulate backdoor attack as a multi-objective problem and optimize with evolutionary algorithm. Finally, later achieves superior performance regarding all our considered attack objectives. That's all. Thank you for your attention. So, any questions?
Yeah, we have time for 2 questions.
Thanks for presentation. So I just want to clarify the thread model. This is data poisoning, or you need to control the training process of the model?
Yes, that's a good question. We need to train the model with the poison data. Actually, in this paper, we consider the black box backdoor attack, which means we don't know finally how the user what structure of the model the user used. But to evaluate our trigger, we need a model to train the trigger to evaluate the quality. So we introduce a surrogate model.
Okay, so the thread model is still data poisoning, right? So it's still data poisoning.
We poison data and train the model.
I'm not really get it. So the thread model is you train the model completely and you transfer the model to the user, and the model is a backdoor.
No, we just design the trigger and poison the data set, and we release the data set.
Okay, I get it. So basically, you use the surrogate model to optimize the trigger.
Yes.
And to make the trigger, then you release the poison data set, and then the other model provider, they can train that model. And in this case, I'm wondering, so what's the poison rate you use? Because the analysis, as I mentioned before, it only needs to poison 0.05%. So what's the poison rate in your case?
Our poison rate is 5%, I think. It's a commonly used parameter in the literature.
Have you tried any lower poison rate? For example, 1?
Let's say if you use like 1%, I think the attack success rate will drop down drastically. But if you use higher poison rate, you will quickly get a poison module, but the functionality, I mean the benign accuracy, will be harmed. So let's say 5% to 10% is a good parameter.
Yeah, thank you.
Yeah, thank you for the question. And any other questions?
I guess no. So let's thank the presenter for this brilliant presentation.
So, thank you.